Perfect evening to everyone. I'm MULIKA Francis from Automotive and Power Engineering. Going to present in Laplace transforms, and my area of concentration is going to be on the proof of Laplace identities as tabulated by the lecturer prior the presentation, and also on the existence and the uniqueness of Laplace transforms. The presentation is going to be short, just like a miniskirt, long enough to cover the subject matter, though short enough to entice. And I'm sure by the end of the presentation, we shall be able to prove on the identities, and on the other side, the existence and the uniqueness theorems of the Laplace transforms. And I think by this time we know the use of the Laplace transforms as we engineers in the field, and we know very well that it is widely used to analyze design control systems. It helps to convert time domain signals into frequency time domain signals, making it easier to analyze and design system behaviors. And more so, electrical engineers do use these Laplace transforms to design electrical circuits. By that, we are going to start by proving our identities, and we are going into the next slide. As tabulated by the lecturer, we are supposed to find for the Laplace transform if given a function equaling to c. When you're given a function equaling to a constant, we first of all have to define the Laplace transform, as we know that when we are finding for the Laplace transform, it is always equal to the integral of 0 to infinity exponent minus st, that function. And we know, as we put in the function as given to us, it is a constant. We are going to integrate from 0 up to infinity exponent minus st times that constant. Then we pull out the constant and integrate normally. By integrating normally and putting in the limits, we are going to obtain to our answer being a c into 1 over s. By this time, the function has been changed from the time domain to the s domain. So by this time, the Laplace transform of our constant c is going to be given by c over s. Then we go into the next. It's going to be given the function t, we find for the Laplace transform. As we know, we first have to define what a Laplace transform by formula, and we know that the Laplace transform is equal to, when we integrate from 0 up to infinity, exponent minus st times that function, the t. Then by this time, the function being given to us is a t, and I'm sure that by this time it's no longer a secret that when we're having a function t being multiplied to an exponent and we have to integrate it, we have to use the by parts. We have to integrate by parts, given a formula of when we integrate u dv equaling to, it has to be equal to u v minus integral of v du, where we are going to choose for a function which is easily differentiated and a function which is easily integrated. And by this time, t is easily differentiated, so we name it as our u. Then the exponent minus st is always easily integrated. So by using of by parts, we're going to continue. Then we feed in, after getting our u and v, we feed in into the formula, put in the limits, and we're going to get a function like this. So it's going to take us to 1 over s out into 1 over s. So the Laplace transform of t is always equal to 1 over s squared. So as we move into the next slide, we are going to find when given a function equaling to exponent minus 80, what do we get? As earlier, we're going to first define for the Laplace transform by formula. And as we've said, it is integral from 0 up to infinity exponent minus st that times that function. And by now, I think we are good to go and everyone can solve this function. So as we punch in the values, then we integrate normally, we are going to see that if you are given a function exponent minus 80, it's going to get us to this point. So when we have that, the Laplace transform of exponent minus 80 is always equal to a 1 over st as our as 1 over s plus a as our final answer, as our identity. Then we go into a next identity, and this is going to be when you given a function t that is in the time domain is equaling to t power n, and they're telling us to change it to the s domain, and that is to get the Laplace of that function is going to be equal, as we defined what the formula for Laplace, it's going to be equal to integral of 0 or integral from 0 up to infinity exponent minus st times that function. But we know the function is t power, and punching in, we are going to integrate again by the use of by parts. Yeah, by parts, and I'm sure that everyone knows the formula. So as we put in the formula, we are going to find that as we go on and go on integrate, the value of n is going to keep on reducing, and down here the s domain is going to keep on increasing. The what? The degree here is going to keep on increasing. So for a function being given t power n, we are going to make a mathematical deduction, and we say that when we keep on integrating, we shall keep on integrating until out of time. So mathematically we deduce that the Laplace of a function t power n is always going to be equal to the n, it's going to always be equal to n factorial, I'm sorry, it's always going to be equal to n factorial over s plus n, being that the n is going to be reducing as we go on, and the degree of s is going to be increasing as we integrate. So whenever we are being given a function a t raised to a certain degree here, we are going to be using the formula this. As we know, when we keep on going, we are going to find that we are not going to do all this, and it's somehow going to be hectic. So we're just going to be punching in the values into the identities. So whenever we are given a t value, a function t being risen to a degree n, it's going to be n factorial, that degree factorial divided by the s raised to a n plus a 1. So we move into the next slide. Sorry. Then we go for trigonometric functions. They are telling us to find for the Laplace transform of sine omega t. And by definition, we know that integral from 0 up to infinity exponent minus st times that function, sine omega t, is going to be the Laplace transform of that function. So we go and we know that at this moment, when we put in the sine omega t, it's going to be integrated again by parts. We know a trigonometric function being embedded with an exponential function being integrated together. We're always going to use the integration by parts, where we are supposed to select the easily differentiated variable to the easily integrated variable. And the easily differentiated variable, we are going to name it as u, and the easily integrated, we name it as the v. So when we go on, we know that when we integrate, we're going to integrate normally as you guys have been doing it at your A level. We are going to see that, let me use a cursor, a laser pointer. So when we punch in the values, we're going to see that our u is going to be equal to sine omega t, and our v is going to be an exponent minus st divided by minus s, but the minus is going to be put this side. Then remember, we are integrating from 0 up to infinity, plus the omega divided by the s. When we integrate from 0 up to infinity, we put in our v. Our v is going to be e. When we pull out the omega s, it's going to be e minus st times the cos omega t dt. Then it's going to when we deduce it, it's going to be to put us on this level. Then we're going to integrate for the second time by parts. So, and this is what we are going to be get. And by this second integration, we are going to recognize that the last integral is going to be similar to our function, the function which we are getting. So we are going to denote this as our Laplace of sine omega, and we are going to equate it because we are finding for the Laplace of sine omega t, and we go on to solve the equation. And by solving, we are going to see that the Laplace of sine omega t is going to be equal to omega divided by s squared plus omega squared. That is for the Laplace transform of, when given, to find the Laplace transform of omega t, it is always omega divided by sine squared plus this omega squared. So we go on to function being equal to cos omega t. As we've solved the previous identity, this is how it is going to be done on this one, because they are all in the trigonometric functions. I think this might be done easily by you guys, so I'm going to skip it. So we go into the hyperbolic functions. And hyperbolic functions, when we are finding for the Laplace transform of an hyperbolic function, it depends on which hyperbolic function is being given to us. So by this time we are being given a sine hyperbolic omega t, and we know from hyperbolic functions, sine omega or sine hyperbolic of an angle is always equal to the exponent of that angle minus exponent of a negative angle divided by 2. So it is this we are going to get and punch. It is this we are going to get and punch into our formula, the definition for Laplace. And we are going to see that when we punch in, we are going to separate the integral. It's going to give us a half into integral 0 up to infinity exponent minus st times the omega times the exponent omega t dt, but a minus integral from 0 up to infinity exponent minus st times exponent minus omega t dt. Then we solve those depending on the laws of indices. We are going to reach out to this. Then solving that, normally we are going to know that we are going to see that when we punch in the limits, we are going to see that it's going to deliver us to a half into 1 out of s minus omega minus 1 over s plus omega as we find for the LCM and do the other stuff. We are going to see that up there we're going to be having a 2 omega. Down here this is a difference of 2 squares. So I'm right to say that s squared minus omega squared is the same as this. So when we are always given find for the Laplace of a sine hyperbolic over omega t, it's always going to be equal to omega divided by sine squared minus minus omega squared. And seeing that you guys are picking the difference when it's not an hyperbolic function, here it is a positive, but when it's an hyperbolic function, here it's going to be a negative. So it's the same application we are going to do with the cosh, with the same application we are going to do with the tan hyperbolic and the whatsoever the hyperbolic functions. So we go on to the next slide. Here this is what I've been talking about. We are going to solve the same way as we solved the other sine hyperbolic. Just for this, we have to know that the cos hyperbolic of an omega t is equal to the exponent omega t, but plus, it's not a minus, it's supposed to be a plus exponent minus omega t. So we patch the whole of this into the definition, the Laplace definition. Where there is cos hyperbolic omega t, we place in this. We solve it normally, we integrate normally. We are going to come to the answer being equal to the Laplace transform of cos hyperbolic of omega t is being equal to s out of s squared minus omega t. And I know you're seeing the difference between cos. So we go into the next. So when they tell us to find for the Laplace transform of a unit stepping function, so they are given that a function is equal to the unit stepping function t minus a. As we know that a unit stepping function is a piecewise continuous function. So if it is a piecewise continuous function, therefore it means that as 0 is for zero values, a is less t is less infinity. Then for 1, t is greater than 0. So we integrate from 0 up to a exponent minus t times a 0 for the 0 values, for the 0 values dt, plus when we integrate from a up to infinity, and from a up to infinity this must be an a up to infinity minus st, it is in the 1, while the stepping function is 1. So the stepping functions for electrical engineers, it's defined as a function which switches on and switches off a circuit. For those who got a chance to pass by a diploma, they did this, and I know that we shall get to know times the dt. Then when we punch in the limits, we are going to see that when we find the Laplace transform of a unit stepping function, we are going to get exponent minus at divided by ace. So for the identities, we're done. As it was tabulated by the lecturer prior the presentation. It was in a tabular form. I've been brief while proving them, but I think everyone has got to know what what really we can do upon them. So when we go to the next, they've told us to find for the to discuss about the existence theorem for Laplace transform. And the condition for the existence of a Laplace transform says that it states that if a function ft is piecewise continuous on every finite interval of the semi-axis as t is greater than or equal to 0, and it satisfies the condition that the modulus of a function has to be less than or equal to m exponent a t for t values being greater than t naught. And for some constants a and m, then the Laplace transform of f exists for p greater than a. I'm sure that by this time we might be somehow confused, but we are going to get it with time. And this condition means that the geometrically that the absolute value of ft does not have to grow faster than the exponential order e alpha t for all values of t. And we know that when e minus lambda t times e minus alpha t is greater than this e. When we come in for this, the times the function has to be less than k. Takes values of k for when we are going to get for the other terms, when we are going to find for defining the conditions. When we are defining the conditions, we know that the conditions are two in this. It has to be piecewise continuous, and it has to be with an exponential order for it to do what? To exist as a Laplace transform. So this condition, that's is the one we are using to see whether the expression is of an exponential order, and the other one we see whether it is continuous. We go into the next step. So we are going to define the two terms for the existence of a function as a Laplace transforms. So the condition one, it has to be piecewise continuous. If for an interval 0 less than or equal to a less than or equal to t less than or equal to 6, there are at most a finite number of points t1 equals to 1, 2 equaling to r, and tk less or equal to tk, and which the function ft has finite jumps stroke discontinuity and is continuous on each such interval tk minus 1, t subscript k minus 1 is less than t and is less than tk, then such type of function f of t is called a piecewise continuous function. So let's get an example to widen our mind on what a piecewise continuous function is. So if we have a function f of x being equal to a series of equations where we have for our first f of x equaling to x squared for the interval 0 less or equal to x less or equal to 5. It means that for the interval 0 less or equal to x less or equal to 5, here the function f of t is continuous. And for the function f of x equaling to t, it's going to give us a what? A jumpy discontinuity, and it means that it has a continuity that, but the value does not go to infinite. It's going to give us a jumpy discontinuity, but it has this discontinuity is there, but the value does not go to infinite. So if the function of f of x is equal to 7, it is going to be in the range of 5 less or equal to x less or equal to 8. And for the function of fx equaling to 9 minus 1, it's going to be in the range 8 less or equal to. As we plot this, we are going to see what discontinuity mean and what continuity means. For the first function f squared in the range of that, as we plot our f of x against x, we are going to see that our first function it's going to be more of a curve since that it is squared. It's going to be more a curve, but it has a stopping point at 5. Then at 5, it's where the second function starts from, and it's going to jump from this side up to this side. So it is going to be at 7 on the x-axis, and 5, it's going to move from 5 up to 8. So I'm saying, I know that you're saying this is continuity from here up to here. It's the jump is continuity. And when we move on to the last function n minus x, we are going to see that it's also going to jump from 8 to 1 when placing the figures into the function. It's going to jump from here up to here. So we are right to say that the function f of x is a piecewise continuous function. Then we go on to the next slide. For the next slide, you're going to discuss about the other condition, that if it is a piecewise continuous function, then it has to be with an exponential order. Then how do we know that this function has an exponential order? It's what we are going to do what? To discuss about. A function f of t for t greater than or equal to 0 is said to be of an exponential order alpha if there exists constant alpha k greater than 0 and t greater than 0, such that when we get the modulus of f of t, the other function we talked about in the previous slides, it has to be less than or equal to k exponent lambda t times for t greater than t. Hence, if a function f is of exponential order alpha, then the limits, when we put in the limits in that functions, when we take the limits in that function as t tends to infinite, we know that the modulus of that function, when we multiply it by the exponent minus alpha t, it has to give us a finite value. And I do want us to take note on this, because it's one we are going to be using to see whether a function is of an exponential order or not. So again we're going to get examples for functions with exponential order. So when we see, if we're given a function f of t, is equaling to t, we're going to see that if t we such that if we see that t, we're going to inspect whether t is of an exponential order. So when we get this t and when we put it in our limits, as t tends to infinity, the function is equal, obviously, what? A t times the exponent minus alpha t. It has to give us a finite value. So when t, if here there is a t, when this t tends to infinity, so it's this t also tends to infinity, it means that the function ft, which is our t, will not grow when it tends to infinity. It's not going to grow faster than the exponential order. The exponential order is this. It's not going to grow faster than that. So therefore, it means if it does not grow faster than this, it's going to tend to a finite value. So when we place in our alpha being equal to 1 and our t being equal to infinity, so we know very well that the value, it's going to give us a finite value. So we have all the rights to say that our function of ft is of an exponential order of 1, since the magnitude of t is less or equal to exponent t for t greater or equal to 0. So I know you're going to go on and we inspect for this being using using our condition there. We go on and inspect for this, we go on and inspect for this as we put in into our condition here. So we move on to the next slide. Example of the functions of which is not of an exponential order. So we have some functions which are not of an exponential order, mostly for the functions which are of exponent, but that exponent being risen to a function, but the function is also risen to what? A certain constant. Most of them, most of those functions are of not an they don't have an exponential order. So when we are inspecting, we are going to see we say that limits for t greater than for t tending to infinity, exponent minus lambda t times that function, it has to give us a finite value for for a function with an exponential order. But we go on and put in our exponent for the function is exponent to 2t squared. So when we solve this by the laws of indices, we're going to subtract, because this is a minus. We're going to subtract. As we do it, we're going to see that it's going to give us a quadratic equation. Then we complete squares. When we complete squares and we try to punch in for our t being tending to infinity, we are going to see that the function is going to grow faster than the exponential order. So it tends that the value this is not going to be tending to a finite value. Then for proof, we are going to see that when we have a Laplace transform of ft, even for the definition that ft equaling to integral from 0 up to infinity exponent minus st function of ft dt. Then when we integrate from 0 up to t exponent minus st function of ft time dt, plus when we integrate t exponent. So we are going to make this piecewise continuous, because it's the same when we integrate from 0 up to t, plus when we integrate from t up to infinity. We've already made this piecewise continuous. Then we punch in the values of ft, and we know that from 0 up to t, this function always exists. It means that it will always give us a what? A finite value. So when we come here, we're going to say we get for the modulus of t up to infinity. It's this. We are going to find for the modulus of t. For the modulus of t up to infinity, it has to be less or equal to when we integrate from 0. It has to be equal to so the modulus, we're going to make the modulus enter the integral signs. So for the modulus, when we integrate from t up to infinity, exponent minus st function of ft dt is equal to when the modulus enter the integral signs. But this has to be less or equal to when we integrate from 0 up to infinity. Automatically you're going to see that if we integrate this cannot be equal to this, because this defines the whole the whole function, but this defines the half of of the function. So it has to be less or equal to this one. Then we go on and put in for the value of f of t. It is the constant k times the exponent alpha t dt. Then when we pull out the k, remember it is still less or equal to k when we integrate from 0 up to infinity exponent minus t into s minus alpha dt. When we integrate normally, we are going to see that for for the value, for the integral of t up to infinity, the modulus of the exponent that function has, it is less or equal to k out of s minus alpha. For the values of s being greater than alpha, it is going to be, for values of s greater than alpha, for values of s, we have to note this, for value of s greater than alpha, the what? The Laplace transform of t exists, and it exists. Uh, then we go on and we see how we determine the exponential order of a function. I've already talked about the condition that when we determine the exponential order of a function, we put in the limits from t up to infinity, exponent minus alpha t times that function must always give us a finite value. Then you can go on and test for this. Then for function of ft is equaling to that, it has to give us a finite value. When we plug in the what? The function, it has to give us a finite value. Then we go on to the examples. We're given a function f of t being equal to, it is a piecewise continuous function, f of t equaling to t out of k for 0 less than t less than k. It is 1 if k is equal to, is greater than k. Then we have that the Laplace transform of ft is equal to, when we integrate from 0 up to infinity, exponent minus st dt dt. So we do what? We punch in the function. We know that when we integrate from 0 up to k, exponent minus st times t out of k dt, it is a plus, because we are going to integrate from this up to this. We know the function from 0 up to k, it is this, and the function from greater than from t greater than k up to infinity is a 1. So integrating this by parts, we are going to go on, and I know by this time everyone is well versed with integration by parts, and this is the last function we are going to be getting. So we solve for the next function. Find for the Laplace transform of f of t. So it is given to us that it is a piecewise continuous. If you see this, you know that it is a piecewise continuous function. So cos of t for 0 less t less alpha. So when we integrate from 0 up to, for this is the definition of the Laplace transform. Definition of the Laplace transform. So we know that from 0 up to pi exponent minus st. So sorry, this was pi. From 0 up to pi exponent minus st cos t dt, plus from pi up to infinity exponent minus st times a 0. So by this, we're not even going to struggle. This is already, it is automatically, it is going to tend to what? To a 0. Then we are left with this. With this, we are going to integrate normally, and I know we are going to reach out to this answer. Thank you very much. Perfect evening to everyone.